Good day. My name is Mark Willis. I'm Head of Integrated Product Support at Pennant International, and this particular presentation focuses on support system modeling and analysis. So what we're going to talk about over the next possibly 40 to 45 minutes is, first of all, a very short introduction to me and Pennant International. Stress it will not be a sales pitch. We'll then talk about support modelling and analysis history and its linkage into the ILS and IPS world. Then we'll do a little bit of background as to why we model support solutions, talk about data integrity, look at the difference between decision making and decision support, look at sustainment analysis, and then I'll summarise and put a few final thoughts out as we come to the end. So let's get on with the introduction then. Okay, a little bit of a potted history about me. I did 34 years in the military, both as a REME aircraft TIFI and then commissioned into the Air Force as an aerosystems engineer. The last job that I did in the Royal Air Force was as the UK head of procurement for the CH-47 Chinook, where I was managing a budget of probably around £600 million. I then left the Royal Air Force and came into defence consultancy, where I've had several board level appointments in SME defence consultancies. I've led airworthiness, safety and certification teams on a number of aircraft, including UAVs. I've held chief engineer roles. My fundamental expertise is in ILS and IPS as it's emerging, as we've modernised the ILS world. I am the senior UK industry representative on the S10000I International Working Group, and I'm a chartered aerosystems engineer and fellow of the Royal Aeros. So that's me. So who's Pennant? As you can see on the slide, Pennant is a market-leading technology-driven business with a global customer base, and we've got offices in UK, Canada, the USA, and Australia. Our software and training solutions designed to enable users to maximise operational and maintenance efficiency, and we ensure systems are where they're needed, when they're needed, and more importantly, that they work. As you can see from the slide, we work about 80% in defence. We have a little bit of work in rail, and we do work in civil aerospace as well. So what we do is effectively in three business lines. We do system support, and that's effectively where our IPS tool sets come in. We have just launched a tool set called Auxilium, and you'll see that in the market going forward. We also do hardware training solutions, so hardware and software training solutions in actual fact, and you can see our training systems in a number of colleges, universities, and indeed amongst the service training establishments all over the world. And in support of our system support, we do technical services. So we put consultancy together, we do support and maintenance, training, and bespoke software development. So getting on to the meat of the matter then, so what are we here to talk about? First of all, support solutioning and modelling itself has a history which goes back in excess of 40 years. As it says on the slide, as young RF officer, I started doing support modelling at CSDE Swanton Morley in Norfolk. That's where I was first started working in the support solutions arena. But coming forward, performance-based logistics, performance-based acquisition, lifecycle support, all started to emerge in the early to late 1990s, but didn't really take hold until the USD Quadrennial Defence Review in 2001, which really stressed the US DoD's wish to use support solution modelling to actually increase the performance of their support systems. We in UK copied, what the US were doing in 2001, and we put together, or started to put together, integrated optimized support solutions. Really kicked off in the helicopter world, then transferred into the fast jet world and the maritime world later on. Land is now catching up, and you will see land integrated optimized support contracts being let in 2024, 2025. It's important to stress at this point, though, that modern approaches go simply beyond modeling the spare solution. Those of you who have been around support systems modeling will have seen tools that will provide you with spares solutions based on availability and cost. But modeling goes beyond that, and there is an emerging discipline which sits alongside model-based systems engineering called model-based product support. And model-based product support solutions are going to be the support solutions of the future. Whether we like it or not, we need to go in that direction. So a little bit of a reminder then about why we undertake ILS and IPS on a project. It's ostensibly to ensure that we influence system and component design and integration from a support perspective. Why do I talk about the integration word? Well, when we're actually looking at a system these days which comprises commercial off-the-shelf items, you would hope that the design work has been done at the production of that commercial off-the-shelf LRU or component which you need to put into the system. However, that's not the end of the story. You need to understand that the way that you integrate your system, the way you put your components into that system, where you position them. If you haven't put any thought in that, you can find yourself in trouble and find yourself spending more money than you need to on supporting your particular system or system of systems. We do ILS and IPS to achieve operational availability at an optimal cost. Bear in mind, I've said optimal cost there, not minimum. Anybody can spend no money at all and get no operational availability, but it's very much in the terms of the best bang for your buck, the best availability at an optimal cost. We must remember that ILS and IPS is a systems design engineering discipline. So we're using it within the by design processes. In our case, we're trying to achieve supportable by design, supportability through design, if you like. That sits alongside the safe by design, secure by design, maintainable by design, reliable by design, all of the other by design principles which fit within that aim to hit the sweet spot in the cost versus performance graphs that we produce. So bear in mind that we're there using ILS and IPS to achieve the supportable by design aim of the design process. And of course, finally, modeling the support solution provides assurance of value for money in your support solution. I tend to use this particular graphic quite a lot, just indeed to actually thrust home why IPS is so expensive. When you look at the whole life cost of a system, the initial acquisition cost is but 20% of the overall whole life cost. It's easy to see. Everybody's out there looking to spend money on the fast, shiny, pointy thing that goes bang. The fast, shiny, pointy thing that goes bang is of little use to you if it doesn't work when you want it. So the total life cycle support cost is as important. And we in fact spend 80% of whole life cost in the support arena. So 20% to actually buy the kit, 80% to support it and dispose of it. So if we're looking to make savings within the whole life cost, savings are best achievable if you start looking at the support costs. Therefore, by modeling your support solution, you can indeed drive down those costs, or indeed, as I said earlier, optimize them. When we're actually looking at the support solution, we need to appreciate the range of types of support solution that there are. And the stairway for heaven in front of you actually shows how we are progressing today in actually evolving our support solutions for the future. We are all probably aware of the conventional support solutions which sit at the foot of this. And by that, by a conventional support solution, I'm talking about the 4 lines of levels of support which we've become accustomed to over many, many years. But as we head towards involving industry more in actually providing our support, then we step up through spares inclusive contracts, through spares exclusive contracts, through contractor logistics support solutions. And there are about 40 ways of delivering contractor logistics support. Heading into where we are today with performance-based contract, so actually contracting somebody to provide us with a level of availability, and then the nirvana for some people is contracting for capability, where in actual fact we contract out for the complete provision of the capability without involving the military at all. And there are good examples of those contracts operating around the world today. So why do we model and analyze support systems? Throughout time, there's become a greater realization that we've got to get a better return on the support investment. Going back to me talking about bang for buck. Based on our Ukraine experience, we've got to be able to outperform our enemies to gain support advantage. And support advantage is in fact military advantage. Support advantage means better than our enemies' operational availability of systems and equipment. And we've focused on that, certainly in UK MOD, in the work that I've been doing recently. There is a focus on support advantage. If we can deliver equipment to the front line more effectively than our enemies, the adversaries that we may come up against, then we will have the advantage in the field. We need to fully understand which levers we can operate to increase our support advantage. What I mean by that is, if we're talking about operational availability, the drivers of operational availability are reliability, repairability, maintainability, and the effectiveness of the support chain. So if you can operate those levers, if you can actually manage those particular areas more effectively than our adversaries, then we can increase our support advantage, increase the operation availability, and have a more effective force. And support systems modeling analysis gives us the ability to fully understand that support landscape. It is a complex landscape. I'm not going to make it sound easy. It is a complex landscape, but by understanding it fully, we actually enhance our understanding of support advantage and how we can improve it. What does a typical model look like? And sitting on the left-hand side of this particular slide, you can see the demand signal. The demand signal is actually what are the operational requirements for our piece of equipment. Included in that operational requirement would be a statement of how much operational availability we require with that capability to acquit our role. The 12 boxes in the center are an example of the type of modelling which you can undertake. And those models, can actually sit as an individual model, or more likely be actually linked together to give you a more complex model, which gives you a better picture of what the support solution performance looks like. As you pop out on the right-hand side, you can see that the output of the model is capability sustainment, or in other words, operational availability. A typical design architecture to enable you to achieve that modeling may look like this. And this is just a typical graphic which I've put together, which gives you some sort of idea. Starting with the transactional data at the bottom, that will feed into some sort of ERP system, and there are a number of good ERP systems out there which are used. Team Center being one, S4HANA. There are others out there which are equally as effective, and the outputs of those are outputs into the finance, commercial, and HR arena. Sitting above that and exchanging information with the ERP system would be the integrated IPS database, which is a logistics support analysis database, a common source database. Typical outputs of that could be information for your technical publications, training, for instance, tool requirements, things like that. Sat above that is a modeling and analysis database. And this is there to actually understand how effectively the support system you're putting together is working. And as you can see on the left-hand side, you've got various support solution analysis, sensitivity analysis, what-if generators, simulation and visualization generators, and all of that will feed out into a set of management dashboards. And the final output of all of those management dashboards will be those data-driven decisions, which you have sat at the top right hand of the slide. That's what we're looking for. That's what we're looking to achieve, is data-driven support solution decisions. Now, looking at modeling and analysis tools, they've existed in defense for over 30 years, in practice, probably closer to 40. Performance-based contracting and initiatives like product lifecycle support, they acted as a springboard for support modeling analysis. But the limitation early on was computing power. We just didn't have enough computing power to use these tools effectively. The support modeling tool market is very extensive today. And it's fair to say that the tools tend to deliver what they say they will. But accuracy and usability rely on, and we mustn't forget this, rely on the following: data integrity, understanding the underlying algorithms, understanding the support system, and the logistic build of the support system. Dropping out of that, the right software product is very important, but the right software product on its own is of little use. What you need to support it is the right people, the right processes and procedures to gain best value from the analysis. And that is equally, if not more important, than having the right software product. Talking about data integrity, it's an old adage: rubbish in, rubbish out. So if you put rubbish into your system, into your tool system, you'll get rubbish out of it. By example, a typical data element we use in support modeling is mean time between failure, MTBF. But you have to consider, so what systems are in place to collect the failure data? How accurate are those systems? How accurate is the data? How's the data passed between the user, the support staff, and the OEM? What are the data protocols involved? How is the data being validated to collect actual failures? I'm sure we're all aware in the support world of those failures which aren't actually real failures, the no fault founds that we find when we return components back to the manufacturer or back to the bay to be serviced. Is there enough data to calculate an accurate MTBF? Bear in mind that MTBFs are derived statistically. In statistics, one needs at least 100 failures to give you a representative population. And if you haven't got 100 failures in there, and it is expensive to gather those 100 failures in the early stages of a component life, then people tend to use estimations. You need to think in your support solutions, if I'm really using estimations, what strategy have I got in my mind to take those estimations and turn them into reality by using in-service data? And how much will that cost me? And you might also ask, finally, is MTBF the appropriate system performance measure to satisfy your needs? There are numerous key metrics out there which you need to fully understand. And you'll understand by taking that data integrity takes considerable effort. And if you get it wrong, can have significant effects on the modeling results. Talk a little bit about decision-making versus decision support. We must not fall into the trap of taking the modeling output as the answer. As much as your software vendor might say to you, what you get out of this is the right answer, treat that answer with the skepticism it deserves. No software tool can replace the decision maker or input from subject matter experts. The adage, if it looks wrong, it probably is a good adage to apply in this arena. Modeling outputs don't predict the future. The data should drive constructive scrutiny. Be aware that mathematics and stochastic analysis has limitations. Professor George Box, a renowned statistician of the middle of the last century, said that all models are wrong, but some are useful. Professor Naira Chamberlain, who's currently working at Atkins, says that the final stage of mathematical modeling is the human rationalization of the output, going back to the if it looks rubbish, it probably is adage. And even IBM back in '79 said a computer model can never be held accountable. Therefore, it must never make a management decision. Too often today, we see management decisions being made on the basis of a computer model output. Without a bit of rationalization, you're leaving yourselves open to failure. But used effectively, modeling and analysis techniques can greatly improve operational availability through data-driven decision making. So use the data to support your decision-making process. Looking now at sustainment analysis. As I said earlier on, spares modeling does not maximize the value of support modeling tools. Confirming your spares requirements okay, but looking at the data as the fleet ages or operational requirements change is more value to actually sustaining that capability. Don't simply update the inventory requirements, but look at your decisions through subjective analysis to complement those modeling outputs. Remember that human rationalization of the model output. Good modeling tools can also quantify risks and benefits by answering key questions. Where's the best location for the spares to be stored? Where should maintenance be carried out to maximize our availability? What's the biggest driver of our system downtime? What variables, levers do I have control over, and how do they affect how we succeed in our mission or how available our equipment is? The bottom line, effectively, is what's the support solution going to cost us? And have I achieved the optimum solution in terms of cost versus availability, bang for buck? So, in summary, then, modeling tools are not there to simply derive a spares requirement in systems acquisition. Unfortunately, that's how they tend to be used. The more effort you put into managing the tools, the data that drives them, the people that use them, the more value you'll gain out of your support modeling. Today, we live in a world where adaptability, agility, the need to do more with less, it's so important. It's what government is asking us to do all the time. But a modeling and analysis capability is incredibly valuable and should attract focus from senior decision makers to better develop the support solution modeling and analysis skills. Finally, then, this subject is being taken so seriously by the UK MOD that they've signed a Support Advantage Charter with UK industry. And this Support Advantage Charter will deliver the defence support strategy. They've recently issued the Support Modelling Analysis Framework, and you can find details of that support modelling analysis framework at the link I've provided in this slide. So, thank you for your attention. I hope you've been able to bear with me all the way through this presentation. My contact details you can see on this particular slide. You see me on LinkedIn very regularly, and I'd be happy to take questions or respond to points via that medium at any time. Thank you very much.